This presentation is titled Applications of Monadic Programming Part 1, Questions and Answers. My name is Anton Antonov. Today is August 3rd, 2025. Monadic programming and monadic pipelines are a relatively simple concept, or at least this is what I think. Some people introduce them in a very complicated manner, and some people think the concept is complicated. Monadic programming was invented a long time ago in the Cold War. Some people think it was a secret knowledge given to us by aliens. I hope with this presentation to clarify some of the basic concepts and about monadic programming and to make it easy to understand. All right, so this presentation is introducing monadic programming through questions and answers. Various examples are used. It is the first part of a three-part series of presentations or lectures. The second part is going to be more linear. In this one I'm going to be jumping quite a lot and scrolling quite a lot in order to answer the questions. And the third part, I'm not sure, probably 60% probability I'm going to make it. It's about programming software monads in Wolfram language. We're using Wolfram language, this Wolfram language notebook. Before going further, I would like to mention that I have these three panels. The panel to the left is a mind map with the questions I'm going to answer. The panel in the middle is the one with the presentation, and the third panel with some additional materials. All right, I have used Mathematica and Wolfram language for quite a long time. You should be aware that I'm somewhat beyond monadic programming. I use it, I program it, I'm not that enamored by it. I started using monadic programming 8 years ago and programming monadic pipelines, software monads. I'm going to expand more on that. And right now I'm not probably as enthusiastic and as dogmatic about monadic programming as some other lecturers might be. All right, so here are the questions. Probably the first most important question is who is the audience for this series of lectures. So for groups, people who want to get informed about software monads, would they program them, would they use them, it's another story. Experienced Wolfram language users or programmers, and this includes also monad developer wannabes in the Wolfram language. If developers from other programming languages want to see how monads are used in Wolfram language, again, this particular lecture is going to be helpful. And all kinds of code baristas, LLM supported programmers and developers, I think they should be aware of monadic pipelines. So how to showcase monadic programming? I didn't delete this, but okay. So I have this data set. This is the well-known Titanic data set. I want to predict survivability of the passengers based on some of the other data I have about them. So I'm going to, I here started a monadic pipeline. I'm going to continue it. So here I'm going to say echo data summary. Let's see what we have. So we have, this is the monadic object here, and I have split the data into 80% for training and 20% for testing. You can verify the ratios here. And then I have echoed that summary, the summary of that splitting data. All right, so I'm going to make a classifier here, and I'm going to use a classifier which is nearest neighbors. And I'm going to compute the classifier measurements. Let's see what we have so far. All right. And so here you can see there's a pipeline value. The value is here, but I want to probably show it here. So I'm going to show this value, echo it, and then I'm going to continue my pipeline with showing the receive operating characteristics. And so basically this is it. So this pipeline, it's a machine learning workflow for making a classifier. I would say fairly concise, fairly informative. If we want to change the classifiers, or if we want to view some other elements here, split the data with different ratios, we can very quickly do that with this type of pipeline. This pipelining symbol, I'm going to explain later on what it is about. But this is a kind of good showcase for this kind of monadic programming I'm going to be discussing. Nevertheless, it's an interesting question when I say applications. What do I have in mind? And in this lecture, I have in mind something more conceptual and methodological than the actual software monads. So the applications of monadic programming, or the reason it is considered useful, or I consider it useful, are these main three reasons. Graceful failure handling, and very often monadic programming is introduced through the graceful failure handling, which is kind of useful for software engineers and software architects, but not necessarily for, say, data scientists. Rapid specification of computational workflows. This is what I was showing here. And this can be supported further with conversational agents and some other techniques. And this is where the third application of monadic programming it comes. It's the algebraic structure of the written code. The code itself, the way you see it here, it has algebraic structure, not the underlying functionalities, not the way the objects internally relate to each other. Like this code here as a sequence of symbols has algebraic properties. This is how I leverage monadic programming in order to do translators and conversational agents that generate executable code, programming code. Okay, so how software monads can be defined? We can have formal definitions and informal definitions. So let me go with the informal definitions maybe. So yeah, long time ago, again, Unix, when Unix was created, very soon after Unix was created, the so-called pipeline, Unix pipeline was invented. I'm going to demonstrate it here. I'm going to clear up here. So imagine, I mean, I'm listing here. So this here is the single application of the monadic pipeline, right? I have all kinds of list of things with the file names which finish with notebook NB, and then I only take those who have monad in it without ignoring the case. And I can also say here make another pipeline pass this information, this file, to the pipeline and say, well, tell me what is the date in which this was created. So this is this first example. This second example is one of the oldest Unix programs. It's called Desktop Calculator, and I'm going to do this. I'm going to do exactly the example how it is written there. And so what you see here is reverse Polish notation, so 3 and then space 5, then plus, then this becomes 8, then 4, then multiply, then becomes we multiply 32 and then we print it, right? So the monadic pipeline, in a sense, here it's the space, and 3 and 5 we can say that they are functions they are functions which represent this kind of values. In Wolfram language, actually, we have something very similar as a construct. All right, so I'm going to expand on this further. So let me move this to another window. And so here with tidyverse, it's an R package or system of R packages in the R ecosystem. And so you can see here, this is a manipulation of the data set or data frame DS Titanic. So we can see here that there's some renaming, there's some filtering, grouping, and counting, right? And so the monadic symbol here is this combination of symbols. I think I'm using a much simpler, a much easier way. It is being shown with my showcasing. I'm using this double long arrow. All right, so this was the informal definition. Formally speaking, I'm not going to go through these definitions, but there are certain laws, monad laws, that have to be satisfied, and you can convince yourselves, you can convince yourself like that these monad laws are satisfied. So we have two operations. One is a unit operation, which if we take something like, say, whatever is our argument is being uplifted into the monad, and then we have some way to bind this particular thing, this monadic object, with some functions, and all of these functions, they return return objects in the same monadic space. So more or less this is what is being assured here. The laws, they assure certain associativity to be held. This means that we can take sub-pipelines of the monadic pipeline. So more concretely, if you want to see how this is being implemented in say, Wolfram language, very simple, right? With fold and bind, right? Fold, bind, mx. So imagine all of these functions, f1, f2, f3, they return symbols which start with m, and they react only to symbols which start with m. And so we can basically have this. In some sense, the postfix notation in Wolfram language does this, right? So if I have this here, it gives me the length of the list, and then I can I can make something like this, and then I can probably do some other function, like for example, why not put this to a third degree and so forth, right? So this is some sort of monadic pipeline. Wolfram language always had the monad laws being satisfied for certain structures in it from version 0.001, I guess. So in more details, you can see some of my videos and lectures from some time ago. I'm not going to expand theoretically too much on this. All right, so let's go back to the questions. How to explain monadic pipelines in a easy to understand manner? Let me actually see here. I probably, like when I was scrolling, this was one of the things to kind of do. And maybe I scrolled in the wrong direction, maybe somewhere here. Yeah, okay, yeah. So let's go back to this classification monad, right? So when I was showcasing, it was actually much easier to get there, I guess. It's exactly under the showcase. So here, this pipeline, what is happening? More or less this is what you see here in this diagram. So I have uplifted whatever data set into my monadic space. I mentioned monadic space earlier. So this is very common in mathematics, right? We start with some object and we put it in some different space, like say how in Fourier analysis we would transform a certain audio signal, put it in the so-called phase space, right? Modify it in the phase space and then map it back, And so this is how your sound equalizers work, right, in your sound systems. So anyway, so here we uplift the data set into the monadic space. We navigate the computations in that monadic space, like, echoing some output time to time, whatever, and then we have some way to get the result back. If I assigned this here to some object, right? And so this is an example here of how I'm getting something back from that object. I can do clcon take classifier, for example. And this is the classifier which I trained. And now I can use this classifier, say, in my other computations in this notebook, which are not necessarily confined to this monad. So this is the reason this is mentioned here, but we map back from down from the monadic space to the environment where we started with. All right, well, actually, I'm not sure how informative that diagram was, right? But in a sense, you can say that, yeah, we have this pipeline value, which is being continuously modified, and with whatever kind of elements here. And so at some point I can get this pipeline value. And so similarly here, this is a different plot. It's basically, we have this pipeline, which different kind of elements in this pipeline, different segments of this pipeline transform what is happening on the pipeline, and then we basically utilize it. More or less this is it. All right, so going back to the questions here. So how can monadic programming be invented? So let me actually find that particular slide here. Okay. As I was showing earlier, I used the Titanic data set. So imagine I have this specification. Now this is a natural language specification, and I'm going to convert this natural language specification into code. But that's something else. We're going to discuss this else. Just kind of clarify all of these codes here in these programming languages. What they mean this thing here. They mean this specification, which should be clear to anyone what it is. So I'm saying that I want to use this data set, DS Titanic. I want to filter by passenger H being greater than 10. And I want to make groups of records with the values of passenger class and passenger sex, and then show the counts. And so here, this is this is how this natural language specification is being translated into different programming languages. So you can see here in Python, Python uses leverages or uses the ideas from tidyverse and about manipulating data, but that's this here. It's very imperative-like assignments. Same with Wolfram language. Is using this monadic pipeline. But let's go to the Python version first. So you can see to the object I'm assigning a copy of the data frame. Then I'm doing some kind of filtering. Then I'm doing some grouping, and then I'm assigning this the size of the individual groups. So you can see what say in some sense. Repeating object after the first line, right? It appears both in the left hand side and the right hand side. Maybe that's redundant. Maybe it's a way it's not necessary, right? And so more or less this is what I is doing. If you actually ignore the prefix deploy, the namespace, right? This operation here, this monadic pipeline in A means that whatever is the argument here, it's going to become the first argument in this subsequent function. And so similarly here, the first argument is being done here, and so forth, right? So more or less, this was what was with this informal definition, or the informal part here, when I was saying that there is like a certain thing which is being modified. There is like a pipeline value which is being modified in a variety of ways. So this is what is happening here. Now in Wolfram language, we have it's something very similar to Python, but this elimination of object, it's probably not that obvious in the way I was describing it, but you can see it's the first argument in the second and the third line. All right, so if you want to see this alive version of this, yeah, I mean this basically works, right? This code here, which was generated, it did actually make the computation I specified with that natural programming language, and this translation routine also works for different languages. So I have been discussing this in other presentations quite a lot actually, and so there is a notebook about this. There is also there's a video which I'm discussing the use of monadic pipelining in data wrangling, and how natural language can be used to translate, to make this kind of translations. All right, so is knowing monadic programming required? Well, no, it's not. I wouldn't say so. You can live quite happily without knowing what monadic programming is. So if I go back to this example here, which is about the invention of monadic programming, right? You don't need to invent the whole algebraic system, right? It's just the monadic pipeline. It's convenient, reduces the so-called syntactic sugar, and it's absolutely not needed. But you benefit with it. Even if you don't know what it is, you might still kind of use it in one way or the other. In my opinion, it reduces the time for knowledge transfer. It's much easier to understand what is going on. Is coding faster or better using monads? I mean, basically what I just said. The workflow management, knowledge transfer, it's much easier. And so, I mean, you can see, like, I have a variety of monadic software monads implemented for different type of things. Like, for example, this here, it's a systems dynamics monad. There's this quantile regression monad, which I'm going to exemplify later on, and so forth, right? Latent semantic analysis and so forth. It's just much easier to do many of these computations in this way. So the other thing, because of the knowledge transfer. So I have written this monadic or software monads in Wolfram language, but I also have written corresponding versions of them in Python, also in R. So this is here in Python, so you can see regressionizer. Actually, regressionizer is here. So this is the quantile regression pipeline. You can see it's the same. It's using the same kind of terminology, or the same workflow, which is going to be in Wolfram language. It's just somewhat, the syntax is somewhat different, but otherwise the workflow is the same. Both of them can be generated through this DSL translation functionalities I'm working on. So going further, is Monadic programming supported in Wolfram language? Yes, and it is supported both out of the box, and you can program it. So let me actually go here through this Monadic pipeline again. So basically, I have in Wolfram language, because it's a symbolic system, we have a way to tuck in this operation, this binding, the application of bind to whatever, right? We can define the symbol double right arrow to apply this operation. And so somewhere here, for example, if I show how the maybe monad is implemented, it's basically, yeah, it's just that actually. So it is pretty simple. I think I'm going to postpone the technical details, but one of the things here is that because Wolfram language can be the function definitions, Wolfram language has an extensive pattern matching language which can be used in the signatures of the functions. And so if you have this kind of polymorphic, if we want this polymorphic behavior when we apply the operations in the monadic space, that's easily achieved. This is one of the ways how monadic programming is introduced, through graceful handling of failure, right? So this is what you see here. This is the very, if not well known, this is the maybe monad, which is quite a lot discussed first when monadic programming is being discussed. Polymorphic behavior, as I said, like, yeah, we can see failure is handled as failure, just passed along. If it is a data set, you do something else, if it is something, if it is some other thing, right, which is some other head, then something else is being done, and so forth. So yes, in Wolfram language, it's very easy to both find monadic pipelines in the language itself, right? This is just using the apply operators and the list operators, or you can extend it in such a way that to be convenient. This is what this Packlet monad makers is doing. It's basically showing how new software monad can be implemented. So it's like if you're interested, you can actually see the actual technical notes and about making a new software monad in the Wolfram language. All right. So how monads are programmed? I mentioned this several times. Basically, just responded to that. So what are limitations of monad programming or using software monads? Well, it's an interesting question. Are people thinking in this kind of sequential manner, right? So are people thinking in this linear manner? In some sense, if you start thinking in this kind of monadic pipeline about your computational workflows, and you are a package developer, right? You're a software developer who makes packages or computational tools. This can put your thoughts in order, your design in order. This also can be very useful, as I said, to do domain-specific languages, which generate code. But do people think in this kind of linear manner? To some extent, this mind map, which I didn't use that much so far, but this mind map shows that maybe this is not necessarily all that linear. We might prefer some kind of charting and jumping between the different type of elements of ideas we're dealing with. Where if you're a data scientist, very often you have to combine different sources of data, different algorithms, and to produce something new. So that's not necessarily something we can say that it's in a linear manner. Nevertheless, right, with monadic programming, some computations easier. And I think for this particular statement, I'm going to use it as a segue to go to can monadic pipelines be combined. Hopefully I have this here. No, I don't. So I'm going to go to communityvolfram.com and I'm going to look for Arabic letters classification. Let me see here. 100 and I think this is an article I wrote some time ago, notebook. Yeah, so 3 years ago. So what I'm showing here, I'm basically using latent semantic analysis monad, and I'm combining it with a classification monad. So I have a bunch of Arabic letters, so like probably 10,000 letters. So I forgot what it is. I think the training set had 5,100 letters for each and 1,000 for the testing, something like that. So I am reducing the dimension, making some manipulations using the latent semantic analysis monad. So basically all these images are being represented in some kind of basis of smaller basis of images, not pixels, or not the pixels being the vectors, the individual pixels, but actually these images. So it's a reduced dimension, and that reduced dimension is being fed to this monadic pipeline for classification, and there is certain systematic search which is happening here. Because I'm using nearest neighbors as a classifier, what is the number of the nearest neighbors, with which result we get the best results. I think it was with four nearest neighbors. And so anyway, but yeah, this is the way to combine one way to combine pipelines of software monads. Now, there's another thing here that in some sense, in order to have this functionality, you need to spend some time to maintain that easy of use, right? And I have seen this both in R and in Wolfram language. I'm not sure about languages which use monads as a fundamental concept, like say Haskell, right? But as I said, I look at monadic programming as a user interface, and then to what degree do you want to do this user interface? I mean, I support it to a large degree, right? And to some extent though, for example, somebody might say, well, but why you have this prefix silicon? Well, yeah, because it's easier for me to do this kind of typing, you know, and I don't want to have these names to be confused with some other names in my kind of environment, like say the global environment. The other is that to some extent this is not the end goal. The end goal is to generate this kind of code using natural language commands, and I can probably demonstrate this. Let me see. This needs to be reloaded, and I'm going to, while we're doing this, I'll probably try to find another example here in which this generation happens. Like for example here, I have this NLP template engine, which with these specifications here, like make a classifier over DS Titanic. You can see how this command here, which was executed, right? It basically generated these pipelines, which are tabulated here below, right? For classification, for the latent semantic analysis, and quantile regression. So yeah, I mean, for me actually, the use of monadic pipelines is yeah, knowledge transfer, easy to manage computational workflows, and rapid specification through natural language specifications. So here, let me zoom in, and so I'm going. This is a little bit of a low level type of user interface, but I'm just copying and pasting certain specification, and because I chose the language to be R, that's why nothing happened. If I choose Wolfram language, we should get the classification pipeline. So, and you know, if you think that I'm using, let me use something else here, right, and generate this again. So you know, we have this 65 double this symbol here. You know, if I copy and paste that code in Wolfram language, I'm going to have valid code, and more or less this was happening. You know, what was happening earlier. All right, so I mean, this service here, the way it works, and you know, it's like I use this to speed up my own work, right? So we are basically somewhere here. No, we're actually here. We're in a certain interface I uploaded in Shiny Apps.io, but I can use this in Mathematica Notebook. This is what with this DSL translation, what I was showing earlier, right? So here, when I use DSL translation, that function uses this web service. Now, I'm renting a certain server in DigitalOcean where I run, you know, this, in parsers and interpreters of natural language specifications, which produce this kind of codes. So if I go back to, say, these examples and take the data wrangling example, let's say I'm going to take this and I'm going to let me remove this part here. So if I do this now is in Wolfram language. If I choose Python, you know, this is going to generate Python code. Same thing. And if I can do this for programming languages, I should be able to do this for natural languages. And so basically, this is what you see here. This has been translated into specification in Bulgaria. All right. So back to the questions here. I think I answered why do I use monadic programming, but yeah, rapid specification and so forth, right? So why did I invest in monad programming so much? There are a variety of answers for this, but if you program software monads, and let me actually find the corresponding diagram here, which I probably browsed already. So if we know the different computational domains and we program software monads for them, it's actually after the software monads have been implemented and the corresponding grammars which generate executable code in that monads, we can see certain analogies. We can see certain, you know, leverage those analogies in some way. And so, to some extent, this is my intellectual interest here. This diagram shows my development cycle. So, the problem domain, you might know it, you might think you know it well, but presumably you learn it better and better. You make the software monad in the way I was showing with the pipeline symbols. Then in parallel or afterwards, you develop a grammar. Actually, you can develop the grammar, right? Grammar for parsing this type of sentences. And I think this was what I was trying to show here. So this here is a Raku package which basically makes all this kind of parsing. And if I show you what it has, so it has this grammars, right, with which the data wrangling is being done and specified, and the parsers, whatever the parser produces, it can be interpreted in a variety of ways, right? So you can see I have different languages. If I go to this Raku, for example, it can have, like, you know, this is the interpretation, what it is in Raku. If I go, I'm going to go to R, because in R I can have two interpretations, of 5 actually, but we can have the tidyverse and the base, right? Base R without additional packages, and tidyverse itself, right? Tidyverse is using the monadic pipelines. Actually, going back here, if you think monadically, you don't necessarily need to have software monad in the programming language you're dealing with. I mean, this is exactly what I was showing here with the data wrangling. In some sense, if you think monadically already, right, you don't need to have the monad support, so to speak. It is you can just generate the code, and so. But, you know, with the software monad, the actual coding, the actual pipelines in the corresponding programming languages are much easier to specify. And you can see, so here this diagram shows that we have as an input different natural and programming languages, and then as an output we go to different programming languages and corresponding packages in them. All right, so let me see here. What else was this? I actually started explaining this. So when did you start using and developing software monads in Wolfram language? So I was teaching a class in 2017, let's say, in Oxford to digital humanities. This was data science for digital humanities. And at the time, it basically, in order to do data science, you had to know programming. It was impossible to the people who had marginal understanding and abilities in programming to actually do anything anything useful with the computational workflows. At that point, I decided, actually, well, we can do something better, right? And you can use monads. Actually, I have a very good example for this. So I'm going to scroll to that example somewhere here. This is the rapid specification. This is the I'm going to explain this too. Now, here, for example, I'm using something called NLP template engine to generate this Monadic workflow. If you see, I assign this to the variable res, and if I say release halt, right, because this was held, you can see you have this computational pipeline. But I can say here that instead of this is a Monadic pipeline, right? The Monadic pipeline looks like this. I just formatted it here. But imagine I say that I want monads to be avoided. All right. So is this code better or easier? I mean, it does more or less the same thing, right? But yeah, it does the same thing, right, as the Monadic pipeline. But absolutely, it is not less clear, right, what it is. So if I go back to the Monadic pipeline, it's much more concise, much more clear what is going on. Otherwise, you can find the fragments here, what exactly is happening, how the plots are made, and so forth, right? Okay, there's I prepared this here about showing why Monadic pipelines can be used, and this is related to to when I started, how the project developed, and what I was saying earlier with using conversational agents. So I'm going to use LLMs for this, right? Now, this particular pipeline, we already showed something like that, but I used nearest neighbors instead of logistic regression. Okay, so here this here is with is using this standard notation, so to speak. Imagine that I have taught LLMs, some large language model, how to generate fragments of this pipeline, and so this is another kind of way to look into the usefulness and the algebraic properties of the code and etc. Right? If I evaluate in place any of this here, so this now went to the corresponding ChatGPT. I think I'm using ChatGPT, and translated that particular natural language command. It translated it into this classifier. I mean, I similarly here, translated it into that command. So because of the software monads, right, the way I can plug and play the different segments, this is actually quite useful. I mean, I can have some arbitrary, so to speak, interlacing of natural language specifications and concrete code here. But natural language specifications, they all also translated into concrete code. All right, so let me go back to the questions. I think I answered all of the questions. Let me see something else here. What is going on? Yeah. And yeah. All right, well, I didn't mention what exactly was my efforts when it comes to Wolfram language with the monads. Initially, yes, I was doing the grammars. Now, I mean, the actual software monads, I said that I implemented them in Wolfram language, R, and Python. So I usually start with the Wolfram language implementation, and then I, move it like 90% of those packlets, this monadic software monads in Wolfram language, 90% of them also reprogrammed into R and Python. But the actual grammars, initially I was doing it with Wolfram language, but then grammars were not that well supported in Wolfram language. It can be supported very well, and yes, we have functional functional parsers and etc. But moving to Raku in 2019 was almost necessary because the grammars can become quite large, and management of the grammars it's important. Also, as I was showing earlier with this Raku package, it is very nicely organized in Raku how you can have certain grammar and how you can have certain actions, right, related to that grammar, how they can relate to the grammar you have defined, and it's very streamlined, very convenient. All right, I think this was all, except I strongly suspect I missed something which I wanted to discuss. So let me scroll through the slides here, and maybe this was rapid specification, the pipelines, quantile regression pipelines, describing here. So in case you got the idea that this was just for data science and machine learning, no. I mean, this here it's a demonstration that this can be done for epidemiological simulations. And so if this basically simulates certain epidemiological simulations, and you can see more details in this software monad called System Dynamics, right? And so how it is done, right? Okay, this was actually related to the question of combining monads. So somewhere here there was a question about can monads be combined, and then one of the answers is not just combining the monads between each other, right, pipeline to pipeline, but also how do we have some suitable algebra of monadic operations, right? And so if I go back to this particular slide, so somewhere here, okay, this was no need to see it in that way. So my first answer, right, was that it can be you can have just plug-in monadic pipelines, and more or less this example here, it's showing something like that. In some sense, there's some elements here, like which are being used into that, like this kind of linear combination. But if you have certain algebra of operations, and this is what these functional parsers provide, right? This algebra operation, so instead of having one monadic operation, which is the double right arrow or whatever, right, I have actually three operations. I have this circle plus, circle multiply, and I have circle dot somewhere here. This is the application. If you think that this is like exponentiation, and of course, circle plus like addition, and this is like multiplication. So what is happening here? I'm saying that I want to parse the phrases numerical integration and symbolic integration. And so the phrase is either starts with one of the two words, numerical or symbolic, and this alternative of these two words is specified with this circle plus, and then it must be followed with integration. So now this here, it's in the monadic space. These are functions, right? So if I show you what this is just a function. If I show you what P1 is, this again, it's another complicated function. It's like we have this sequential composition, alternative composition, and so forth, right? So all right, so these two are parsed. I can make a full-blown parser which parses sentences like numerical integration of whatever function or whatever range, right? And if I use this parse apply, also shortcutted with this circle dot, I can make a full-blown interpreter. So you can see here, I am basically have created an integrator of a natural language commands. So using a natural language command. So this here it's going to be let me see, X, A, and B, right? And produce the same results. Okay, more about this can be seen in this Packlet functional parsers. All right, I think this was all, and yeah, thank you for your attention.